So, hello and welcome. In this workshop, we will design magnetic switch or MagSwitch in 3 dimensions. In MagSwitch, we have two solid cylindrical permanent magnet. Diameter of each permanent magnet is 12 millimeter, height is 5 millimeter, and the material is neodymium N52. We have also a high permeability house, which is made from Hiperco 50 material, and its length is 24 millimeter, width is 14 millimeter, and height 5 millimeter. And the pool shoe dimensions are 24 millimeter for the length, 14 millimeter for the width, and the height is 2 millimeter. And also the material is Hiperco 50. And finally, we have the workpiece, or let's call it the target. The length of the workpiece is about 24 millimeter, width is about 14 millimeter, and height is 5 millimeter. And the material of the target or workpiece is steel M19. So let's go to Maxwell software and step-by-step design or do the electromagnetic design for the MagSwitch in 3 dimensions. We need to build a parametric model to change later any dimensions of the design, or to do a specific study on the effect of each parameter on the force of the MagSwitch. So let's do the model as a parametric model, and step by step do the design. So let's go to Maxwell here and click on project. Sorry, we need to start here a new project, and let's rename this as permanent magnet switch 3 dimensions, and go here to project and click insert Maxwell 3D design. Let's call this also MagSwitch 3D. And let's start with the two permanent magnets. As we said, here we have two cylindrical permanent magnets. So let's draw the first one as shown here. This is the first cylindrical permanent magnet. Let's call it the upper permanent magnet. Upper permanent magnet, and I will give it a light blue color. And let's define the meter here to be d cylindrical, divide by 2 because this is the radius. And as we said, the diameter here for the cylindrical permanent magnet is 12 millimeter. So let's put here 12 millimeter and click OK. And the height, let's call this height of cylindrical permanent magnet, and the height here is about 5 millimeter. Let's click here OK. And for the position of this permanent magnet, I will put here height of cylindrical permanent magnet as shown here like this. Let's click here on fit all to see the permanent magnet, and I want the coordinates to be large. So let's go to view coordinate system and click here large as shown here like this. So this is the upper permanent magnet. Let's draw also the lower permanent magnet. Let's call this the lower permanent magnet. And the height for the lower permanent magnet will be the same, also same dimensions, but for the position you will put here 0 millimeter and click OK like this. So this is the upper permanent magnet and this is the lower permanent magnet. So let's assume that the lower permanent magnet is made from a material called neodymium N52. So let's select the material from here, N52 material. And for the orientation, I will make the orientation for the lower permanent magnet on the positive direction for the y-axis. Here the material coordinate system is Cartesian, and click OK like this. And for the lower permanent magnet, let's assign also N52, but with negative orientation in the y-axis. So here N52, and let's clone this material and put here negative y-axis and just put here -1 like this and click OK. So in this case our switch will be in an off condition. So let's call this design as off like this. So now we already have the two permanent magnets. Let's go to draw the house. Simply the house is a rectangular. Let's draw a rectangle, a simple rectangular like this. Sorry. And we will call it a house, and it should have a gray color like this. And let's define here the house length in the direction of y-axis. So the house length should be about 24 millimeter. And let's put here in the X size, the house width. The house width should be 14 millimeter. And click here OK like this. And for the house height, it should be the same as permanent magnets. So we can put here the house height, and actually the house height here is about 5 millimeter also, same as one permanent magnet. So I think the house here should be 10 millimeter. Sorry, let's put the dimensions here for the house 10 millimeters like this and click OK. Now we just need to reposition the house to be exactly in the center. So for the x-axis I will put here minus house width divided by 2, and for the y-axis we can put here minus house height divided by 2 also, and click OK like this. Sorry, this is in the y-axis the house length, sorry, as shown here like this. And now we need to subtract these cylinders from the house. So let's take this cylinder here, copy them and paste them like this, and select the house and the new parts for the permanent magnet, and go here to edit boolean and then subtract, and we need to subtract the new parts from the house as shown here like this. So now we have here this is the house, and these parts represent the permanent magnets. So let's assign the material for the house to be pure iron, or here the material, sorry, Hiperco 50. So let's call this Hiperco 50. Let's select here Carpenter Hiperco 50 material. This is a steel material with high permeability, and click here OK as shown here. So this is a house now, and these are the permanent magnets. In the next step, we need to draw the ball shoe. Actually, the ball shoe is also a rectangular, but this rectangular is located below the house, and this ball shoe is very important to direct the magnetic flux towards a workpiece or the target. So let's simply go here and right click on an empty space here and select faces, and select this face here and go to edit and surface and create object from face like this. Now we just need to extend this face along the negative z direction with -2 value, or minus or with the ball shoe height. So let's go here to edit, and let's we need to extend this, so we go to sweep along axis here, along vector, and this should be in negative z axis like this. Here in draft type, select extended and click OK. Sorry. Just here we need to put 0 and 0, and here the ball shoe is about the height of the ball shoe is about 2 millimeter. It should have the same dimensions of the house, and here let's call it height of ball shoe, and this will be here length and 2 millimeter like this. And we just need to put here negative sign and click OK like this. So now we extended the house as shown here. This is known as the ball shoe of the MagSwitch, and actually we can select both the house and the ball shoe. Let's rename this first as the ball shoe, and let's select the house and the ball shoe and go to edit boolean and select unite like this. Now we need to draw the target or workpiece exactly below the MagSwitch or the house here. So let's draw another rectangular. Here let's select the XY axis like this and extend it in negative direction. So let's first write here the workpiece piece, or okay, and let's give it a color as gray color here, and assign this workpiece. Sorry, before assigning the material, we should put here the dimensions for this target. The width, the length of the target is 24 millimeter. So let's put here target length 24 millimeter, and for the X size we will put target width, and target width is about 14 millimeter, and for the height let's put target height, and is about 5 millimeter, and for the X and Y axis we can put here minus target width divided by 2, and here minus target length divided by 2, and for the Z axis let's put minus pool let's put here, sorry, I will keep it 0 right now and go here. The height of the pool shoe is about 2 millimeter. I just need this name, and let's put here minus height of the pool shoe, and click OK like this. Now this is the workpiece directly located below the MagSwitch as shown here, and this is the MagSwitch. Let's go here to selection mode and select objects and go around the model like this. I think we just need to put here also minus target height to be like this, okay, to avoid any interference between the MagSwitch and the target. So now what is the material of the workpiece? The material is steel M19. Material is steel here, M19. So I will select this material, M19 29G, and this is the pH curve characteristic for this material, and let's click here OK like this. Now let's go to the definition of our model. We should start with the solution setup. It's here magnetostatic, and we can go here to draw and insert region and put here 150. Bed all directions similarly and click OK as shown here. This is the boundary or the box that encloses our electromagnetic design, and after that we can select all parts here and go here to assign mesh operation and choose surface approximation and select here suitable resolution for the solution setup. Also we can go to analysis here and add solution setup and just increase the percent error here to 3 instead of 1, and keep the remaining setting as the same and click OK. And now we need to assign parameter here to the workpiece to measure the force at the workpiece. So let's hide now this box for the boundary and right click on the workpiece and go to assign parameter and click here on force and click here OK like this. Actually the main effective force is in the that direction. So I will go here to create magnetostatic report and click on data table and plot the force in the select the data report for the force in Z direction. So now let's check that everything is okay for our design. As I said, here the switch is in off state because the orientation of the upper magnet is in opposite direction to the orientation of the lower magnet, and the magnetization direction here is diametrically. So let's run the model and measure the force. And after that, we can also plot the magnetic field density map at the MagSwitch in case of off condition, and also simulate the MagSwitch in case of on condition. Actually, this will take some time, so I will pause the simulation and return once it finishes. So now the simulation is finished. The force at the off condition is about 840 millinewton. I will select here Newton instead of millinewton. So it is actually very small force. Okay, we can now select here all parts like this and go to selection mode and select or extend selection and select all object faces and go to fields and select here the magnetic field density to plot the magnetic field density for this model. Actually, we can see here that the target or the workpiece is in dark blue. We have here a very little flux goes through the target piece, and this flux actually is the reason for this little force. We can work on it to minimize this force. Okay, but this force will be negligible if compared to the force in the on state condition. So now this is the magnetic field density map for the off state condition. Let's now drag this model here to make a new model, but for the on state condition. Just the difference between the on state and the off state is that in case of on state, the direction of the permanent magnets will be the same. So we can, for the upper magnet, we can drag this upper magnet from here just to here. So both magnets have now the same orientation in the positive direction for the y-axis. So now let's run the simulation in case of on condition and see the force value to compare it to the force in case of the off condition. Let's here hide this box, and also I don't want the grid here, and I don't want the ruler, and let's hide the coordinates also. Now this is the magnetic field density map in the case of on. You can observe here the clear difference between the on state and the off state. The force at the on state is about 98 Newton, so it is a high force if compared to the force in case of off state. So simply by rotating the upper magnet by about 180 degree, we can turn the mag switch from the off state to the on state to attach the target or the workpiece. So actually, this application is very important in the MagSwitch is very important in different applications like robotics and welding applications, and to hold any steelwork piece. And it's actually very useful in many applications. So I hope that you like this video, and see you in next videos.